I am delighted to host the Distinguished Speaker Series, and I am super excited about our guest speaker today. Our speaker today will be Prashant Shenoy. Prashant Shenoy is currently the Distinguished Professor and Associate Dean in the College of Information and Computer Sciences at the University of Massachusetts at Amherst. He received the B.Tech degree in Computer Science and Engineering from the Indian Institute of Technology in Bombay. And he did his master's and doctoral studies and has a PhD degree in computer science from the University of Texas at Austin. His research interests lie in distributed systems and networking, with the recent emphasis on cloud and green computing. He has been the recipient of several awards, including a Sigmetrics Test of Time Award. He serves on editorial boards of several journals and has served as the program chair of over a dozen ACM and IEEE conferences. He is a fellow of the ACM, the IEEE, and the American Academy for the Advancement of Science. I opted to see what Google Scholar had to say about Prashant. Google lists 452 academic publications that were cited an incredible 23,045 times. Just an incredible body of work. Speaking of energy and sustainability, Prashant will be presenting a carbon-first approach for zero-carbon computing. This is highly relevant to Juniper's green-to-the-core commitments that we have made. So please help me welcome Prashant Shenoy.
Thank you, Patrick. Let me just share my screen and we'll get started. So good morning, good afternoon, good evening, depending on where your location is. I am really delighted to be presenting this talk at Juniper's Distinguished Lecture Series. Thank you, Patrick, for that kind introduction, and thank you also for inviting me to this industry seminar series that Juniper is organizing. So what I will do is get started with the presentation, and I look forward to a lot of discussion at the end of the presentation during the Q&A. As Patrick mentioned, this talk focuses on a carbon-first approach to zero-carbon computing, and it is largely focused on the issues of sustainability and the related issue of climate change. So let me first talk about these and then get to what this talk is about. So as we all know, the effects of climate change have been accelerating. There have been numerous extreme weather events in recent years, everything from flooding in cities to wildfires in California to tornadoes and hurricanes that seem to be getting stronger and more frequent. And there is now substantial scientific consensus that these effects are as a result of climate change, and that our society needs to think about decarbonizing aggressively and reducing its emission if we have to limit the impact of what climate change is going to do to our society in the coming decades. So this graph here shows what the different trajectories for global carbon emissions look like depending on how we reduce or do not reduce our carbon emission. So the top curve, which is in the red, says that if we do nothing and continue to be on this unsustainable path, global temperatures are going to rise by 4.9 degrees Celsius, weather problems are going to get worse, ocean levels are going to rise, and things actually get really bad. But on the other hand, if we implement decarbonization strategies and successfully reduce emissions, we can be on the blue curve, which is at the bottom, which limits the rise in temperatures globally to 1.5 degrees Celsius. That is what the United Nations Climate Council thinks is a more sustainable path for society as a whole. And then the question before us is, can we actually be on the blue path as opposed to any of the other paths that are shown in the picture, which actually cause much worse problems in the future? So with that introduction to the problem of climate change, let's talk about what computing has to do with this. So let me first talk about this exponential growth of computing infrastructure that's shown in the graph at the bottom. That graph actually shows the rise in cloud computing platforms year on year from 2008 to 2020. And you can see that there is a near exponential growth in cloud computing. And this has largely been driven by the success of the internet and mobile devices being ubiquitous and all services being on the cloud and so on. So this has really been the defining technology trend of our time. Now, if you look at this growth and ask, okay, how has energy usage of computing infrastructure in general and cloud platforms in particular grown over time, you see a different picture. Okay, despite this near exponential growth, energy usage of this computing infrastructure has actually grown a lot more slowly. And this has largely been because of very aggressive energy optimization techniques that have been adopted by data center operators and cloud platforms and so on. And that's shown in the picture at the bottom right, which shows you this metric called power usage effectiveness, or PUE, which is a data center metric for energy efficiency. And you see that that metric has actually gone down over the years despite the growth in cloud computing platforms. And that has allowed these platforms to grow without actually a substantial energy impact. But what that figure on the right also shows is that energy efficiency gains have largely stalled. And in any case, PUEs cannot reduce below the optimal levels of 0. So going forward, there aren't a whole lot of energy efficiency optimizations left for us to continue with these types of improvements. So let's look at what the future is going to bring. Now, cloud computing platforms continue to grow significantly year on year. This growth has largely been driven by data-intensive and AI workloads. Now, if you look at AI workloads, specifically machine learning and deep learning workloads, these are actually been doubling every 3.4 months for a number of years. So that growth is much faster than anything else that we have seen in terms of application workloads in the recent past. And cloud platforms cannot sustainably meet this demand with the current types of infrastructure that we have. So the figure on the bottom left shows you the size of deep learning models and how they have grown year on year. And keep in mind that that's a log scale on the y-axis. So a linear growth in the size of machine learning models indicates an exponential growth in their size. And this is coupled with the workload itself doubling every 3.4 months. So as you can imagine, this is only one class of workload. But if you actually look at the cloud infrastructure in general, the growth is going to continue and is going to actually accelerate. And this is going to cause a very high growth in energy and carbon usage, because as I argued on the previous slide, there are not a whole lot more energy optimizations that you can actually extract from these platforms. Now, computing industry as a whole, if you look at its global carbon emissions, it's actually on the order of 2 to 3%. And that's the pie chart that's actually shown on the right, which shows that there are many other sectors like transportation and manufacturing and building operation that consume a much higher amount or generate a much higher amount of carbon emissions. Cloud computing and computing infrastructure is a small part of the pie, but it's growing really quickly. So if we do not do something about this problem, that the emissions from this sector is actually going to start becoming much bigger than what it is today. So this is a good time for me to introduce a couple of terms and try to explain what terminology we are going to use in this talk. So first, I'm going to introduce the term energy efficiency and carbon efficiency. Now, energy efficiency is something all of you already heard about, most likely, and we'll define it as the energy consumed per unit of work done, unit of computing work done. And people have worked on energy efficiency in the context of mobile devices and servers and data centers for decades now. And lots of the energy efficiency gains have come from technology improvements. Now, carbon efficiency is a different concept, and we'll define it as the carbon dioxide generated per unit of work done. Now, it's important to realize that carbon efficiency is not the same as energy efficiency. They are related concept, but they are not the same. So just to give you an example, an highly energy efficient system can still be carbon inefficient, if it actually consumes energy that comes from brown sources. So it's highly energy efficient, but its carbon footprint can still be high if the energy it's consuming is not green. So this should give you some understanding of why these two terms are not one and the same. They are definitely related, but they are distinct. And what we would really like to do is to design systems that are both energy and carbon efficient. So with that understanding, let's now look at the carbon impact of the cloud workloads and specifically the growth in AI workloads that I was talking about, and try to understand how much carbon emissions might they generate in the future. Now I'm going to present two views that have been articulated in the community, in the research community. So first is this pessimistic view, which is articulated in this graph, and it was in a very highly cited paper that was published 2 years ago. And what this graph shows is, it shows you the carbon emissions from different types of activities. So there is an airline flight that you can take from New York to San Francisco. That's the first bar. There's an average consumption and carbon emissions from 1 year of human life, and then 1 year of that human life in the US, which tends to be much higher. Then we have a bar that shows how much does your car emit in a year that you drive it around. And then the last bar, which is the highest, is how much carbon emissions are generated from training a single machine learning model. And you will see that that is much higher than all of those other activities. And that should give you some sense of how carbon inefficient AI workloads are today. And if you look at how they are increasing in terms of doubling every 3.4 months, that gives us a very pessimistic views of how much carbon emissions are going to be generated from just the AI workloads, and hence from cloud workloads as well. Now, there's a different viewpoint that industry and specifically Google has articulated recently, and there's a paper that has just been published by Dave Patterson and several other colleagues at Google, where they have claimed that the carbon footprint of machine learning training is going to plateau because there will be aggressive energy efficiency improvements that industry will put in place, and then eventually it will start shrinking. So this gives a very different view of what cloud workloads might look like in the future from the perspective of their carbon footprint. Now, regardless of which view you subscribe to, the pessimistic or optimistic view, there's clearly a lot of work to be done, because no one here has actually said how are we going to actually get to zero eventually. And this is just talking about what it might look like in the future, but not how we will actually get to something that might be sustainable. So the question I'm going to address in this talk is, what kinds of techniques might we be able to employ to decarbonize computing infrastructure and all kinds of computing and cloud workloads like AI and many others. And this is very aligned with the mission that we have at the University of Massachusetts, where we like to look at research that focuses on computing for the common good or the societal good. So with that motivation, the rest of the talk is going to involve first talking a little bit about what decarbonization actually means. And I'm going to present some of our work on a project called Carbon First that's looking at decarbonizing cloud computing. And I'm going to end with several future challenges of what remains to be done both within the research community and in industry. So before we actually get started, it's instructive to look at all kinds of press releases that you may have seen in the recent years and try to understand what they mean. So for example, if you actually go and look at press releases being put out by large cloud companies or companies that operate very large data centers, you will see that Facebook says that it's reached net zero emissions. Amazon claims it's the world's largest corporate purchasers of renewable energy. Apple claims it's powered by 100% renewables worldwide. Google claims it's been carbon neutral since 2007, which is 15 years ago. So if you look at these press releases, you might wonder, saying, have these companies already solved the problem? What is remains to be done? Are we already there yet? And what I would like to do is to look at the terms that are actually being mentioned in these press releases and many research articles and try to define them a little better so you can get some sense of what has actually been done and what remains to be done. So let's start with the term carbon neutral. So when someone says that their organization is carbon neutral, what this effectively means is that they are buying carbon offsets from the energy market. And in some sense, they basically consume energy that still has substantial amount of carbon emissions, but then you go and buy carbon offsets from a market to offset the impact of emitting these emissions. So as an analogy, this is equivalent to someone driving a very inefficient car and polluting, but then paying a penalty for pollution. So you're paying to emit carbon emissions in this case. And the next term is being net zero by using 100% renewables. So in this case, my organization, what they do is organizations go and enter into long-term contracts with renewable energy sources like wind farms and solar farms, and they buy the output of these renewable energy sources. And what this effectively does is it covers the electricity usage from that organization for a year. So over the course of the year, the generation from these renewable sources is equal to the consumption from that organization, which effectively means that you have a net zero in terms of your carbon energy usage. So what this does is it actually reduces your emissions, but as I will show you on the next slide, it actually does not eliminate. And then there is another term that actually has entered the lexicon, which is carbon free. And this has been a concept that Google introduced not too long ago, where they essentially say they are going to use carbon energy at an hourly granularity, whereas the previous concept of net zero was trying to use zero carbon energy at 1 year granularity. And I will explain what the difference between these two is on the next slide. Now, in this talk, I'm going to use a different term, which is called zero carbon, which is the strictest of all of these, which basically says that you're going to use zero carbon energy at all times, not just at a year granularity or an hour granularity, but maybe at a second granularity at a very fine time scale. So as you can see, there are these different concepts of what it means to be green. As we go starting from carbon neutral, which basically says that you are going to emit carbon emissions and then offset it, and all the way to being zero carbon, which means you actually have a zero carbon footprint at all times. And most companies have actually addressed the first two of those bullets. They're either carbon neutral or they're getting to net zero via 100% renewables. And we are really a long way off from being either carbon free, which is doing this at an hourly granularity, or zero carbon, which means that you never emit to begin with. So there is quite a bit of work to be done. And so you should really look at these press releases as actually starting down a very long path or a journey to getting to zero carbon. So in this slide, I'm going to explain a little more what net zero using 100% renewables means. So there is a graph that is shown here, which looks at a data center, and the green curve shows you the energy generation from some renewable sources like, let's say, a wind farm or a solar array. And you will see that is highly intermittent because all renewables are inherently intermittent. The energy generation depends on how hard the wind is blowing or how much sun is shining and so on. And then the black line there shows you the actual data center demand, and you'll see it's roughly stable over a long period of time. Now you will see that there are actually periods where the green curve is much higher than the black, which means that you are generating enough renewable energy to completely cover the consumption from that data center. And there are other periods where the green curve is much below the black curve. And these are periods where there are gaps in carbon-free energy and you are underproducing. And so what net zero essentially means is the total amount of generation that you have from your green source over a whole year is actually going to be equal to the total consumption. But it doesn't mean that you are actually going to cover all of your energy needs from that renewable sources at all times, because there are times where you have deficits and there are times when you have surpluses, and the two effectively cancel out each other over this long period of a year. But what this also means is when you have a deficit, you are going to consume energy from the electric grid, which might come from other sources like natural gas or coal, and you will still actually emit carbon dioxide. So it's not really completely zero carbon. And to go to true zero carbon or carbon free, you need to do this matching at a much finer time scale than 1 year. So you could do this at an hourly time scale, which means every hour, the amount of energy you generate from carbon-free sources equals your consumption. Or you can do this at second time scales, which is even harder. In either case, this is going to significantly increase your cost of energy generation because you need massive over-provisioning of renewables to ensure that you have enough energy to power your demand at all times. Or you need other sources like nuclear, which are going to give you zero carbon energy, but enough to sustain your minimum workloads. Now, all of these techniques that I have been mentioning, they are well known in industry, and industry is working on them. But if you think about it, they're all electric grid side methods, or what we will call as energy supply side method. So you're really trying to figure out what sources of energy are you going to use to power your operation and how to make those sources carbon free. Now, in this talk, I'm going to talk about a completely different side of that equation, which is the demand side of it, or demand side optimization. So as I already said, supply side methods involve switching to lower carbon energy sources. And we looked at carbon offsets and carbon matching and all of these techniques. But there is a whole other part of this equation, which is demand side methods, where you can actually try to change your operations or modulate your demand to reduce emissions in the first place. And this is what I'm going to focus in the rest of this talk. And this is especially interesting for computing workloads because many of these workloads tend to be elastic in nature. They exploit the flexibility, or we will exploit the flexibility in the workload to reduce emissions. And our view is that both supply and demand side methods will be necessary if you want to get to true zero carbon in the future. So with that, let me now switch to giving you some idea of how this can be done. So at UMass, we have a project called Carbon First that we have been working on that focuses on decarbonizing cloud computing. And one of the key goals of Carbon First is to make carbon efficiency a first-class design concern in both hardware and software. So we don't want to now build systems in the future that just focus on performance, which is making things faster, or reliability, which means they don't fail as often. We also want designers to think about making them carbon efficient while thinking of these other design metrics. Now, with that high-level goal, our Carbon First has 4 key focus areas or sub-goals. The first of which is that we want to expose the energy and carbon usage to applications and systems. Because currently data centers and cloud platforms don't really tell you how much energy you are consuming as an application or as a cloud customer, and how much carbon impact that energy usage has. And we want to make that information available. Second, we want to provide carbon control mechanisms to enable applications and customers to modulate their carbon usage. And this is going to be a key technique for our demand side optimization that I was just talking about. Now, given these 2 mechanisms, we would like to enable all kinds of flexible policies that both applications and customers can use to optimize their carbon usage. So in short, we want to promote demand side methods that maximize the use of zero carbon energy. So what I'll do is we'll actually look at how some of these things can be done one step at a time. So let's first think about how electricity is consumed and what carbon impact it actually has. Now, it's important to realize that the carbon emissions from electricity is actually going to depend on the source of that energy or the generation source. So 1 unit of electricity that's generated from a coal plant is going to have a very different carbon footprint when you compare it to 1 unit of electricity that comes from a solar array or a wind farm. And typically when the grid supplies energy to a data center or to your home, the carbon intensity of that electricity is actually going to be dependent on the mix, saying how much of that energy was sourced from a natural gas plant, how much of it came from green sources or hydro, nuclear, or whatever sources are being used in the by your electric utility company. And what this picture here shows you is that carbon cost of energy is actually going to vary from one region to the other. And in this figure, the countries that actually, or states that have green, are actually sourcing their energy from relatively green sources, and where you see them being yellow or brown is where they are actually getting sourced from sources that are more carbon intensive. So the carbon intensity of energy is going to vary from one region to the other. But more importantly, even within a region, the carbon intensity of energy actually varies over time. And that is shown in the second graph here, where you see, let's take the blue curve as an example. That's the carbon intensity of electricity supply in the state of California. And you will see that carbon intensity is actually varying on an hourly basis, and actually varies by a factor of 2 from one day to the other, or from some parts of the day to other parts of the day. So this is something that we want to keep in mind as we try to perform demand-side optimization. Now, interestingly, there are already commercial services like Watt Time and Electricity Map that are exposing to you what is the carbon impact of the electricity you consume from the grid. So this information is now available to computing applications and software and to cloud infrastructure. So what our carbon first approach is going to do is it exploits the availability of green energy across space and time. And the idea is that we want to optimize the carbon usage of cloud applications. And the way we will do this is that we are going to shift our cloud workloads from high carbon periods to low carbon periods. And that is going to exploit that time variation that's shown in the first graph. Or we can shift these workloads from high carbon regions to low carbon regions, depending on which areas in the world actually have low carbon usage. And we can do this by using any global cloud provider. And you see the Amazon footprint on that second figure there, and shift your workload from one region to the other, assuming that your workload actually allows such elasticity. So we'll use these two observations and we'll try to see how they can actually allow cloud applications to reduce their carbon footprint. So let's start with how you can first expose carbon and energy usage to the application. So to do this, our project is developing what we call the energy hypervisor for the cloud. So in this case, our energy hypervisor can monitor the energy usage of containers and virtual machines that are running either in a virtualized data center or a virtualized cloud platform. And this hypervisor exposes this energy usage and the carbon impact of that usage all the way to operating systems and applications. And this is done using performance counters and using IPMI interfaces to monitor server energy consumption, and the use of models that translate some of that energy consumption and apportion it across containers and applications that may be running in your infrastructure. So once we have exposed the carbon and energy usage to applications, we would now like to also give these applications some control over how much energy and carbon they are using. And our energy hypervisor also has an interface that now allows applications to control their carbon consumption. And this can be done in one of two ways. The indirect method allows applications to control their resource usage. And by controlling their resource usage, they can control their energy and hence carbon usage. So one way to think about this is an application that might use elastic scaling techniques such as horizontal scale. So in this case, an application can horizontally scale up or down to control the number of containers and servers it is using. And by doing so, it can actually control how much energy it consumes across all of its containers and servers, and hence how much carbon it consumes. And there are already techniques such as C groups in Linux that allow you to control this programmatically. as well as container orchestration platforms like Kubernetes that also allow you flexibility in performing such control. Now, the direct method that our hypervisor provides is to allow applications to specify a cap on the carbon rate that they are consuming. So in this case, the application might say it wants to ensure that its carbon usage never exceeds a certain rate. And then the system will enforce that rate using standard networking and operating system techniques like token bucket control or fair queuing techniques that are already used in many operating systems and networking products, such as what Juniper makes as well. And so in this case, the applications are actually focusing more on their carbon usage, and then the system actually enforces that carbon usage through internal resource control mechanisms. And our hypervisor allows rich interfaces to enable both of these methods, depending on whatever makes sense in a particular data center or cloud environment. So assuming now we have these interfaces, it is instructive to see what kinds of policies we can implement with these interfaces. So now I'm going to explain how you can control, or how an application can control its carbon footprint via the concept of time shifting. Now, these type of techniques are more suitable for batch jobs or data processing workloads that have time elasticity, which means they don't have strict latency SLAs. There is some flexibility in their completion times and so on. And what this figure that you see on the left shows you is a technique called wait a while that was proposed by researchers in Europe last year. And the basic idea is that the carbon cost of energy is going to vary over time, and that's shown in that blue curve in the figure on the left. And what this technique does is that it essentially pauses computations when the carbon cost is high, and it resumes the computations when the carbon cost is low. And you will see that in that figure where the valleys in the graph are marked as low CO2 periods, and that is where the workload will actually execute on the server. And at other times, you basically just pause your computation. Now, this is only going to work if you have batch workloads that are tolerant to such pauses, and you have some flexibility in how long they can take before they complete. And now it turns out that this type of technique is actually useful in many regions of the world where you see this kind of carbon intensity of energy. And the figure on the right actually shows you that this is true, for example, in California. And this figure is called the famous California duck curve, because it looks like a duck. And it's essentially the carbon intensity of electricity that is generated by California grid. And you'll see that during the day that carbon intensity goes low, because there's a lot of solar generation in California. So there's a lot more green energy during the day than in the evening and the night. So you have more green energy in certain hours than other hours, and that's what you should exploit if you want to reduce your carbon footprint. Now, this kind of technique, of course, reduces your carbon footprint, but it comes with a significant disadvantage. And because these are essentially pause and resume methods, where you may pause your computation for hours at a time, it can significantly increase your completion time. And some of our experiments showed that that increase can be as much as 7x or 7-fold increase in how long your computations take to run while reducing your carbon usage. So that may not be an acceptable trade-off for many applications. So what we have done is actually extended this idea to employ continuous scaling. So rather than pausing computations when the cost is high and resuming them when the cost is low, we will scale down our computation when the carbon cost is high, but continue to compute at some lower rate, and then opportunistically scale up when the carbon cost is low. So this means that you're going to use a lot more servers when the carbon cost is low, and a lot fewer servers when the carbon cost is high. And the graph on the bottom actually compares how this technique performs with regards to the previous technique I mentioned, which was wait a while. We call this technique a wait and scale. And effectively, there are two types of bars here. There are two y-axes. One is the carbon emissions, and the other is the completion time. And you will see that you can actually match the carbon emissions of the wait a while approach, which is the white bars, while significantly reducing your completion time, which is the pink curve and actually getting or overcoming the limitation of pause and resume approach. Now, we implemented this technique for machine learning training because I previously mentioned that AI workloads are essentially growing quickly and are carbon inefficient. So the basic idea was to exploit the elastic nature of ML training and use more resources during low carbon periods and less resources during high carbon periods using this concept of continuous scaling. And we looked at how this would perform in different parts of the world. And you see 3 different countries here with 3 different types of curves in terms of their carbon intensity or carbon costs. And I have one such result on the right, which is actually showing how this would perform in California. The red curve is the carbon intensity, and the black curve is the amount of computing resources that are used, and hence the carbon footprint of those resources. And you will see that the 2 curves are out of phase or inverted, which means whenever the carbon cost is low, the black curve is high, which means you're using opportunistically more resources to compute more during low carbon periods and keep your carbon emissions low overall. And these techniques resulted in this particular graph, 45% resulted in a 45% reduction in carbon usage while giving you similar completion time as doing nothing at all, which means that you are carbon agnostic. Now, there are several challenges in implementing these techniques, and I'm going to talk about them quickly. And the main challenge comes because you're trying to opportunistically scale up during low carbon periods, and that's not always possible. In the ideal case, if you double the number of resources or the number of servers you give to an application, you expect this performance or throughput to also increase linearly, and that's the black line in the curve in that graph that is on the slide. But most applications don't have this ideal behavior because they have numerous software and hardware bottlenecks, which means that the actual scaling is going to be sublinear, which is the blue curve, or non-linear, which means that increasing resources may sometimes not get you any benefit at all if you hit some kind of a hardware or software bottleneck. Now, if you don't take these effects into account and you naively scale up during low carbon period, you are actually going to make the problem worse. Your carbon efficiency will actually get worse rather than getting better because you are using more resources, but it's not giving you a speed up in your application because you have other scaling bottlenecks. So when you implement these kinds of techniques, you have to carefully understand how well your applications can scale up and then use that kind of behavior judiciously to implement optimal carbon aware scaling. And this is really an open question at this point as to how do you do this for all kinds of workloads. And we only seen one example here in this talk, which was an AI work. So let me now talk about spatial techniques for implementing carbon control. And these kinds of techniques are now, in this case, going to be targeting geo-distributed cloud services as opposed to batch applications that I was talking about earlier. In this case, we are assuming that you have some sort of a cloud service or a large application that is replicated in multiple geographies, and it's running in multiple data centers on the cloud platform. The basic idea here is to shift your workload to cloud regions that have more green energy at any given time. So you will move your workload from cloud data centers that have higher carbon footprint energy to data centers that have more green energy. And one way to think about this is you're essentially following the sun or following the wind, because there's always some part of the world where the sun is shining and the wind is blowing, and that part of the world has plenty of green energy available at that point in time. So if you could move your workload to those regions, you can do the same amount of work, but at a lower carbon footprint. Now, doing this kind of optimization requires geographic load balancers that are carbon aware, so they can send your work or move the work to replicas that have local green energy. Now, this kind of technique also needs to be done carefully, because if you blindly move all of your workload to locations that have the greenest energy, that might come at a very high performance cost, because it may be the case that the green energy that is being generated at the current time is in a far off data center. And if you move your workload there, your cloud service will see high latency to requests that are coming in. And these are web-based services that have low latency requirements. So you want to perform this redirection in a performance-aware manner, which means that you want to limit the amount of redirection to some regions that are within a radius of where the requests are originating from. And what the graph at the bottom shows you is how much benefit you are going to get in terms of reducing the brown energy consumption as you increase the radius. So as the radius increases, you have more flexibility in how far away you can move your workload, and you can get more gains, but that comes always at the cost of higher and higher latency. So you want to balance these trade-offs in order to get optimal geographic load balancing in terms of getting good performance while also getting a reduction in carbon usage. So again, these are techniques that are being looked at both within our Carbon First project as well as researchers elsewhere. But this gives you some idea of how you can use or exploit spatial differences in the availability of green energy to reduce the carbon footprint of cloud applications. So having explained how you can exploit the elasticity of cloud applications to reduce their carbon usage, let me now move into the last part of the talk, where I'm going to talk about open challenges that remain to be addressed. Now, as I already argued earlier, the path to getting to true zero carbon is actually a hard one. And there are numerous challenges that both researchers and industry will have to address in order to get there. The first question you could ask is, how do some of the ideas that I explained today generalize beyond cloud workloads and the cloud industry? And the answer is, it's not an easy generalization, because cloud workloads are actually the easiest ones to address, because many of them have this type of elasticity I talked about. Not every workload is going to be elastic. Not every computing infrastructure has this elasticity. So for example, if you are an ISP that has a lot of networking equipment, your routing equipment may not have this kind of elasticity where you can actually reduce the resource usage of your network infrastructure and so on. So there's a lot of work to be done to understand how do you actually address these types of problems in the context of inelastic workloads, which might be seen in other industry beyond the cloud. The second issue is, how are you going to limit the increase in complexity from making computing carbon aware? So it should be clear from the examples I provided that we are making applications a lot more complicated, because they have to decide when they should compute, when they should pause, when they should scale up or down, or when they should move the workload to other regions. All of that is going to actually make application design and system design a lot more complex. And you don't really want to do that by developing tools that make it automated or easier for developers to use, while also taking advantage of the carbon reductions that might come from implementing these techniques. And one other challenge, which is an important one, is to consider the life cycle carbon costs. Everything that I talked about today focuses on only one aspect of carbon usage, which is the operational carbon. All hardware and software products have also what are called embedded carbon costs, which is maybe the carbon cost of manufacturing the server that the software runs on, or the carbon cost of the networking equipment that is used in the data center and so on. And understanding this embedded or lifetime carbon cost is just as important as operational carbon costs. And I didn't really talk about the embedded carbon at all today, even though that's a really important issue to keep in mind. And last but not least, one of the open questions is, how can you combine the supply and demand side methods that I talked about in this earlier in the presentation to get to zero carbon? The techniques I mentioned in Carbon First are purely demand side. A lot of what has actually happened in the cloud industry has been mostly supply side methods. And as I said, you really need a combination of both to get to zero carbon. So I'll have a few thoughts about these open challenges, and then I'm going to conclude. And one interesting data point that I want to mention here is this extreme design point that we are thinking about, which is, can we run computing applications solely using renewable sources? So no grid power at all. And this is really a challenging problem. And it's really one point in the design space where you say, okay, you have only renewables, they're highly intermittent. There are 3 graphs at the bottom that shows you the generation from a solar array. And depending on how cloudy or how sunny it is, the generation is going to keep fluctuating over time. And then the question is, can you modulate your demand to match that supply curve and stay under that supply curve at all times? Okay, and this is not going to be an easy task, because as the energy supply is going to dip, you will not have power to power all of your servers, because you cannot fall back to the grid if all you have are renewable sources. At most, you might have renewable sources and energy storage batteries that might allow you to mask some of these fluctuations. Now, if you want to eventually just use renewable energy, which are intermittent in nature, you actually have to rethink how you design your applications to begin with. In other words, you want to think about how to design reliable applications that run on an unreliable energy source and an unreliable computing infrastructure that is powered by these sources. So that brings me to this notion of transient computing, which is a concept that systems researchers have looked at, including in our group. And what transient computing assumes is that resource availability is going to actually fluctuate over time for any number of reasons. In our case here, the resource availability fluctuates because you may not have enough energy to power your server or networking equipment. And that will cause resource unavailability, which is a type of a failure because your servers are not available to run your application. So how can we tolerate these failures using fault tolerance techniques, high availability methods, replication, all kinds of distributed systems and networking techniques that have been developed, but in a different context? Can we use that here to actually mask this energy supply volatility and essentially use only green renewables to power our equipment? Yeah, there's no answer to this question yet because this is an open research challenge, but it explains the kinds of problems that we have to think about in order to eventually get to true zero carbon and handle energy volatility that the grid itself is going to face when it supplies energy to computing infrastructure elsewhere. But the figure at the bottom right shows that this is possible to do, but has been studied in a different context, which is cloud spot markets. And using fault tolerance techniques, researchers have actually developed ways to tolerate resource outages and yet keep the application running and give good response times. So the question is, can we use some of these ideas in this context? So with that, I'm going to actually conclude this presentation. So what I argued in this talk is that computing systems need to become more sustainable in the future for us to get the computing sector as a whole to a zero carbon footprint. And I also said that to do this, we need to make carbon efficiency a first-class design metric for both hardware and software developers. And in this talk, I showed you examples of how you can exploit elasticity in computing workloads to reduce the carbon footprints of cloud applications. And clearly, there's a lot of work to be done to implement similar ideas for all other kinds of workloads, including non-elastic ones, as well as non-cloud applications. And I'm going to end by saying there are significant challenges that we as a community, both the research community and the industry, have to address in the coming decades to get us to that point where we can say that we have a very large amount of computing infrastructure, but all of that is highly sustainable and has a zero carbon footprint. So thank you very much for all of you for your attention. I'm very happy to take questions, and I'm going to leave this slide here where I want to acknowledge all of my students and collaborators that actually contributed to many of the research ideas that I presented. Thank you very much.